We have a responsibility toward Pierre Leroux and his family, and you're going to say a few words about what this is about.
So when Pierre Leroux retired, he made a speech, and he said that behind every scientist there is a woman, a wife, and she is very important for scientific life. So I think it would be a good idea. You are welcome to sign a postcard for the wife of Pierre Leroux. I have written in French what I say in English, and don't lose time by looking at the other side of the postcard and looking if you are beautiful on the picture. But so just sign and be careful. The paper is a photo paper, so if you have a pen with ink, which so I put a pen which does not, and you have plenty of time the whole afternoon to do this, or row by row. Thank you very much.
Okay, so our first speaker today is Kurusch Ebrahimi-Fard from Haute-Alsace, and he will speak on solving Bogoliubov's recursion and renormalisation using a simple algebraic identity.
Okay. First, let me thank the organizers for this invitation, and of course I'm very sorry about the fact that Pierre Leroux cannot be here. I never met him, but I was very much looking forward to do so, and it's quite sad that he's not here. Okay, so let me start by first underlining that this is joint work with José Gracia from Zaragoza, Dominique Manchon from Clermont-Ferrand, and Frédéric Patras from Nice. And okay, to start with, let me put the things into a historical order. And so what I find so interesting is actually that these things somehow fit together following actually the period of time when the works I try to put together to arrive at saying something in the context of the work of Kohn-Kreimer about the Bogoliubov recursion, that the works which are relevant actually appeared in the mid-50s. By commutative setting, I really mean commutative algebra, where certain identities appeared related to the work of Spitzer, Schützenberger, or Schützenberger, Baxter, Atkinson, and Rota. And this is all about essentially the Spitzer identity, or so-called Rota-Baxter identity in algebras. And there's also the work by Cartier and Fuata, and especially Cartier in '72. In non-commutative setting, I mean really non-commutative algebras, associative algebras, and there's the work of Magnus and Fair and Wilcox. There's Gelfand, Kropp, Lascaux, Leclerc, Retac, and Thibon. And it's essentially about initial value problems and solving them or giving a solution in terms of the exponential. And well, the motivation and application is actually saying something about the original work of Bogoliubov and Parasuk in the context of perturbative renormalization. And essentially the right setting, the right algebraic setting is actually the Hopf algebra approach to renormalization, somehow discovered by Dirk Kreimer and further developed by Kreimer, Broadhurst, and Kohn around 2000. So I have to say something about renormalization. So the goal is I would like to extend functional identities for so-called Rota-Baxter algebras into the non-commutative setting, which means for non-commutative algebras. Essentially, many of them were known for commutative algebras, and somehow having the application to renormalization theory in mind, we have to understand them in a non-commutative setting. The main observation is to do so, actually we have to use a particular type of a non-associative algebra, a so-called Preli algebra, which is quite natural in the context of non-commutative Rota-Baxter algebras. And actually the setting in which we would like to say something about Bogoliubov's counter-term recursion is Kohn-Kreimer's Hopf algebra of Feynman graphs. I don't want to bother you too much with Hopf algebra theory. Simply I remind you here of the main actually structure map, which is the co-product in this Hopf algebra, and actually the convolution product, which is defined in terms of this co-product. And to somehow make this more transparent, we simply will go through a concrete calculation. So we want to do renormalization theory in the setting of Hopf algebras. So first of all, we have this space of the algebra of Feynman graphs. Don't worry too much about what's the product. I mean, it's this joint union. And we see the Feynman rules as simply a map associating to a graph a certain element in a commutative algebra A. And we want on this commutative algebra to operate a linear application, which we call R. Okay? So now here you see this is a Feynman graph. Here you see the rooted tree associated with it. And essentially what we would like to calculate in physics is the so-called the map phi plus. Here we have phi, and actually we want to associate with phi a certain map phi plus. And how are we going to do this? Actually, we take the image of phi, and we take the image of this graph under phi, and we subtract actually the image under R. So it's a simple, naive subtraction. We call this term the counter term, and this is, at this order, actually, this is what renormalization can achieve, and this is the good expression we are looking for. Now going to something more complicated, take this graph here, which actually has the same type of graph sitting inside it, which is actually represented by this rooted tree with these two vertices corresponding to these two subgraphs. The whole procedure is almost the same, except that we have to prepare this expression before we can actually subtract something from it. Essentially what you see here is we have to do this kind of more complicated operation on this graph, where you can see that somehow there's an extraction procedure, which I indicated here by the cross. We somehow extract this simple one-loop diagram. Then actually multiply this with something we have calculated in lower order. This is this counter term, which comes from this first order term, actually corresponding to this one-loop term. We can do this twice. We can extract this one, or we can extract both of them. Then take simply the product. Here, of course, somehow we have to say something about what this means, but we will come to this later. Once we have done this, actually somehow this goes under the name of Bogoliubov's preparation map. Somehow we have actually taken care of these subdivergencies here. Then we simply take the whole expression, take the image under R, and subtract this. So after all, it's a naive subtraction, but somehow we have to prepare this expression before this works, actually, when we go to more complicated objects having these subdivergencies. So here I indicate this operation, which is Bogoliubov's preparation map, by a phi bar. And then once we have calculated this slightly modified thing, we can simply subtract from it the image under R, and this is what physicists would look after, the renormalized expression. Okay? So again, we call this whole thing of this graph, which means the image under R of this preparation, we call this the counter term. And now let's have a refined look on this expression, actually, in terms of the renormalized expression, phi plus. So here we have this so-called counter term. Here we have this expression, actually, which you see here inside which is in the argument of R. Here I multiply by 1 in the algebra A. And so now let's somehow disentangle the whole thing, okay? Here I already wrote it in the good order. We simply somehow put the maps to the left-hand side. Here you have phi minus, which always operates actually on the subgraphs, which we have extracted. We have phi on the right-hand side. You see we always have the phi on the right-hand side. And then we put tensor products here. Here you see we have kept the ones, and we take in the end the product in A. Okay, so we have actually this decomposition of the graph. Here we do nothing, or you can say here we extracted the whole graph and replaced it by 1. Here we didn't do anything. And here we do this operation twice. We first subtract, say, the upper subgraph, then the lower subgraph. Of course, I mean, somehow I only kept one of them, and I put the 2 here. And here we extract both at the same time. Okay? So now this whole procedure, abstractly on the graphs, we call the co-product on this space of the algebra H, which actually makes it a Hopf algebra. Okay? This is what I call now the co-product. And now we can somehow rephrase the problem of calculating phi plus, the renormalized amplitude, simply by first doing this disentangling via the co-product. Then we apply on the left channel this co-product map, which obviously always operates on a lower degree diagram, somehow a diagram with lower number of loops. And on the right-hand side with the original Feynman amplitude, which also operates on a graph with a lower number of loops. And we somehow call the whole thing star. This is actually the algebraic formulation of this phi plus calculation.
Where did this come from, that you multiply to the right and 1?
Here,
Yeah.
this one,
This is on the left, but it's on the right.
here. I just simply, I'm in A, so I simply put 1 times A is A. Just to show you where the 1 comes from.
Didn't have any meaning.
No, it didn't have any meaning. Just so to motivate the 1 here. Okay. Of course, it goes together with the question whether 1 is mapped to 1. But I mean, that's in
Sorry, what was the MA again?
MA was the product in A.
Ah,
Okay. So let's put this into a theorem, just for the sake of completeness. Actually, this is one due to Kohn and Kramer. They actually found on Feynman graphs this unital graded connected associative, commutative, co-associative, and non-co-commutative Hopf algebra, essentially characterized by this co-product. Again, here you have this part where we actually almost do nothing on the graph, and here we have the part where we extract the subgraph. Okay? Then, as I mentioned in the beginning, we have Feynman rules, which are simply associating with such a graph a certain element in an algebra A. This algebra is supposed to be commutative and unital, and especially these Feynman rules are supposed to be multiplicative. This is important. And we want A to be equipped with a certain, what we call a renormalisation scheme map, simply a linear operator operating on A. Again, now the space of linear functionals, somehow the maps associating to H a certain element in A, can be equipped with this product A, which I tried to motivate on the slide before, and it actually makes this space an associative algebra, but non-commutative. Okay, here again you have the co-product, here you have the two linear maps mapping going from H to A, and then you multiply in A. And the problem of renormalization is actually calculating phi plus, and here are the recursions. Simply reformulating these more complicated expressions when you look at them actually when applied to a diagram. Here we can rephrase them purely algebraically. This is in an associative algebra, the one equipped with this product. Here we have this counter term map. Here we have phi minus 1. This is the one for this convolution product. And phi plus, essentially, as you can see it now, here we have the map R and the identity minus R appearing. You can simply verify this. You expand this expression, and you find this factorization which we observed for the concrete example we had before. Okay, somehow the whole thing has been rephrased in terms of these two recursions. So if you want, essentially, this so-called counter-term recursion, where here this is this Bogoliubov preparation map, abstractly written in terms of the convolution product, which we defined in terms of the co-product in the Hopf algebra.
I'm a little bit confused about the tensor product. What does that mean, or what spaces are being, is that living in, or?
I mean, this is simply the tensor product of H with itself. Okay?
So does that correspond to like the incoming line, the outgoing line, or?
No, it's simply taking the tensor taking the two Hopf algebras, I mean taking the algebra and tensorizing with itself. I don't know, it's really simply, I don't know what you mean. But maybe it's not important. Okay? So, okay.
We have another question. With R,
Yeah?
at the moment it's just.
We'll come to this. We will come to this. It's the important point.
Right.
Okay?
There will be just a certain collection of R's which have a meaning finally.
We will see. Okay? So, again, I started with the Feynman rules. This is somehow which characterizes the quantum field theory. And I didn't tell you actually, as there are multiplicative maps, they are sitting inside the group with respect to this convolution product. So as we have seen, this map phi plus actually could be written in terms of this product as phi minus times phi. So the natural question would be maybe whether we can characterize phi plus, respectively phi minus, actually as a factorization of these Feynman rules. For this, we would have to show actually that phi plus and phi minus are actually themselves sitting in this group. And well, remember we had this explicit recursion for phi minus, and what we would like to show is that it's itself a multiplicative map. Now, for showing this, actually, Kohn and Kramer were forced to somehow put the constraint on this map on A. They called this the multiplicativity constraint. So we want actually R to satisfy this identity. As an example, for an algebra A where such an operator exists, actually take the Laurent series and the projector to the strict pole part. Now,
What was A again?
A was the target space of these Feynman rules. So, and for the moment,
Okay.
an associative, commutative, unital algebra with such a map. Okay. With such a map, so supposed to satisfy R. This actually you need, if you want to show that this recursion gives a multiplicative map, you need R to satisfy this identity. Okay? So we have abstracted the problem of renormalization. I mean, you saw this concretely with these diagrams, etc. But the problem is we want to rephrase this in terms of a factorization problem, and we can see the whole thing as actually something like we are working in a non-commutative associative unital algebra, which I write here as A with this product, we take a certain element here, we take 1 minus the element we had before, we had phi minus 1, and we have a certain linear map R which we want to satisfy this identity, and then we are looking actually for solutions for explicit expressions for these recursions. Well, a natural expression, of course, is simply the iteration, which what you would call in a different context maybe the Dyson-Chen series. And again, we have also another recursion or equation, I mean here we have x, where we have the mapped identity minus R, such that in the end we factorize z, which is 1 plus a, into x inverse times y inverse. This is actually what we want to show. Now, first, there are a couple of observations. Once you start with such an algebra, non-commutative and associative, you see immediately that the identity minus R also satisfies such an identity. Moreover, you see that if you have these two recursions, here in terms of R and R twiddle, and of course here it's important we're in a non-commutative setting, then you immediately have this factorization property. It's an abstract result which is true in any algebra with such an operator, associative. Okay, so this is x inverse times y inverse. Here I tell you the equations for y inverse and x inverse. They will become important later. So let's look for examples where we can learn something about this type of algebras. Take so far in the commutative setting the integration by parts rule. Okay, remember there's the Riemann integral, a certain function algebra, associative, and you know that the product of integrals satisfies this identity. Where do we use this identity? Take this simple initial value problem, transfer it into an integral recursion. Okay, this is essentially what we had here. But you can immediately guess there's something about this term here. I will come to this a little bit later. And you know that the formal solution is simply the Dyson-Chen series, but of course you also know that you can write this explicitly as the exponential of the integral of a. And why is this true? Well, simply take the n-fold power of the image of f under I, then this is essentially due to this integration by parts rule, n factorial times the n-fold iteration. This kills the n factorial in the exponential, so you're left over with this sum here. Now, let's come to the non-commutative setting. Of course, this is not anymore true then. So again, start with this initial value problem and the associated integral recursion. Then it was Magnus in 54 actually who insisted on the exponential solution, and he proposed the following element omega and the differential equation for it. Here you see the adjoint operation with the Lie bracket and the Bernoulli numbers appearing. Okay, and here I remind you of the Bernoulli numbers. And you can also characterize it simply as taking the logarithm of the Dyson-Chen series associated to y. Okay, so but we will actually focus on this fact. Here you have the Lie bracket. Here you see this is omega point, this is the derivation, and here we have the integrated one. Okay, so that's the important thing. And let's look at them a little bit closer. So we develop the first three terms. Here you have the Bernoulli number 1 over 2, 1 over 12. Then, I mean, you can explicitly expand this, and so you get this iterated Lie brackets combined with integrations and these coefficients. Let me remind you also of a formula. I mean, maybe it's called continuous Baker-Campbell-Hausdorff formula. Goes back to Plebanski, Mielnik, Strichardt, and maybe other people with particular coefficients, sum over permutations, strictly iterated integrals, and these Lie brackets here. This we will use later. Now, let me remind you of what's called a weighted integration by parts identity. Again, in a commutative setting, this is somehow the classical work. And it goes back to Glenn Baxter from 1960, not the famous Baxter, but it's still the same identity if you put it into a Lie algebra context. Essentially, he was starting also with the classical initial value problem, but then he said, look, let's focus on the integral recursion and add this extra term here with a weight parameter in the underlying base field. Okay, we call it theta. And then his motivation actually came from the work of Spitzer, coming from fluctuation theory. This is what's called Spitzer's classical identity. Again, you can give an explicit solution to this recursion. Again, it's essentially the point is here we don't want to work anymore with differential equations because there are examples of such algebras, as you remember from this projector, where there are no derivations at hand. So you have to stick to this recursion. And this is actually the recursion you also saw for the renormalisation problem. Here you see again, it's relating actually this so-called, if you want, generalized Dyson-Chen series, like the iteration of this integral equation, to the exponential. But here you see the difference is we have the logarithm appearing. If you simply take the limit for theta going to 0, you see we get back the original explicit exponential solution for such an equation when theta is 0. Okay? So this is, but this is of course only true in the commutative context.
So on the right hand side there has a theta, but left hand side doesn't.
Huh?
In this box.
Yeah?
Right
It's hidden in the identity for R. Here you take product of R, so you get theta appearing. And this you want to actually cancel. That's why the logarithm appears. Okay? So let's have a closer look on this identity. So we have this identity here, and then we compare this actually with the exponential and the logarithm expanded. So we go to degree 2. You see here, this is actually the Rother-Baxter identity in a commutative context when you put the 2 on the other side. If you go to degree 3, it becomes a little bit more complicated, but you see essentially how a strictly iterated expression is re-expressed in terms of products, either products of R maps and products of the arguments, okay, with this coefficient. And when you look at this, actually, remember the weight 0 case, this was simply then n factorial, the strict iteration is the n-fold product. Now if you take this weight theta different from 0 into account, you get back, you find what's called the Boden-plus-Spitze identity. We take such an iteration, n-fold iteration, for n different elements. We apply the permutations, and then you find this expression in terms of products. Here the sum runs over unordered set partitions. Here you have the parameter theta appearing. And of course, in the former case, if the n elements are equal, then you have n factorial, and you have to divide by n factorial on the right-hand side. If you take the case n equal 2 for 2 different elements, you get essentially the Rother-Baxter identity itself. Of course, up to the fact that this is in the wrong order, but in a commutative case, it doesn't matter. Here, for A1 equals A2 equals A3, you get 3 factorial, and then you get this decomposition we had before. Okay? So let's give this thing a name. We call such algebras with such a linear map R a Rother-Baxter algebra of weight theta. This can be associative, can be a Lie algebra, and the Lie algebra actually appears in the work of Semenov-Tianshansky. Anyway, let me remind you of the observation we made first. Here now I put the minus theta. This is because here we have a plus. The map R tilde actually is also such a Rother-Baxter map, so it satisfies the same equation when you put the tildes here. And the image of R and the image of R twiddle are subalgebras. This is indicating this factorization property. Let me remind you of the first example, which was actually this projector in the for Laurent, a series with a finite pole part. We actually project out the pole part. Another example are the Q difference equations, where you have this sum actually satisfying this Rother-Baxter identity of weight -1. We have the summation operation corresponding to finite differences. And so there are 2 algebraic structures which will be important now. First, so let's start with a Rother-Baxter algebra and define this new product. Define in terms of the map R. Okay, so you take this, you take the weight theta into account. Then actually the underlying vector space equipped with this product is again a Rother-Baxter algebra. Okay, so it's again, say the algebra, the beginning was associative. This is again an associative algebra. If it was a Lie algebra, it's again a Lie algebra. So you keep this structure, but so you have a whole hierarchy of such structures because again, you have a Rother-Baxter algebra with the original map R being the Rother-Baxter map for this new algebra, by what I mean for this new product. And we call this the double Rother-Baxter algebra. And immediately going back to the Rother-Baxter identity, you see that R set is an algebra homomorphism from the algebra with this new product to the original algebra. And for R tilde, you see it's almost the same up to this minus sign here. Now, there's a second structure, and this is somehow, which is only interesting actually when you go to the non-commutative setting. You can also define a pre-Lie algebra structure. A pre-Lie algebra is simply a vector space with this binary composition, which is supposed to satisfy this identity. So, okay, it's like you have the associator here on the left-hand side, and then you have on the right-hand side the associator, but you have switched the order of A and B. So it's what's called a left pre-Lie algebra. And for and now let's focus on the associative Rother-Baxter algebra. You can define this composition. You simply take the Lie bracket of x and y, but on the left-hand side you apply the R map, and you subtract theta yx. Essentially, you can rewrite this in this term. It maybe looks very close to the associative or to the double Rota-Baxter product I introduced, but here you change the order of x and y. Why is this important? Because if you anti-symmetrize such a pre-Lie product, you get a Lie algebra. So it's a little bit finer than a Lie algebra. But again, for an associative Rota-Baxter algebra, we have this double Rota-Baxter structure, and we have this pre-Lie Rota-Baxter structure. Let's get back to the Magnus expansion. For the moment, we focus on the weight 0 case. Remember, we wanted to find an explicit expression for this integral equation. This was the differential equation for this Magnus expansion. Here I do this expansion. Here you see, I mean, as theta is 0, we have actually a Lie bracket. We are somehow in a weight 0 Rota-Baxter algebra. So we have the Lie bracket. On the left-hand side, we apply the integration operation. So we can reformulate this actually as a pure recursion in terms of the derivation of omega and using the pre-Lie product. So it's a rewriting of the original Magnus expansion in terms of this pre-Lie structure. And here somehow we replaced the adjoint operation by this pre-Lie adjoint operation, right? Which simply means taking the left product with this Lie, with the Lie product here, okay? Here I remind you of what it means. So the natural guess is that if you want to extend this to the weight theta case when theta is different from 0, it's natural to assume that you simply replace this pre-Lie product by the pre-Lie product in the weight different from 0 case. And this is actually the theorem we were able to prove, that when you are in the associative Rota-Baxter algebra, then actually you can define this exponential. Here's the exponential with respect to this double Rota-Baxter product, which is associative again. And then you can show that this omega prime, it's not omega dot, because somehow the notion of derivation is not at hand here, which is the solution to this recursion, which is almost like the recursion we are looking after, but there's an R mapping. Somehow we have shifted the R map a little bit here. Then you find that omega prime satisfies essentially the expansion as the original Magnus expansion, except that we write now this pre-Lie adjoint operation, okay? And again, you have the Bernoulli numbers appearing here. Here I remind you of the associative product and the pre-Lie product.
What's the difference between the omega prime and the omega dot?
Well, this is, if you want, this is a formal expression. There's no derivation. It's not a derivation, okay?
So it's just defined then?
I just call it phi omega prime to remind you of the origin, which is the differential equation due to Magnus for this omega, okay? I mean, if this was essentially your original algebra with the Riemann integral, you would get back what you would expect. But essentially for an ordinary Rota-Baxter algebra, there's nothing like a derivation, but simply it reminds you of the origin. So now a remark, actually what this theorem tells us is that Bogoliubov's preparation map, you remember this was this counter term map convoluted with phi minus 1, so that you get this counter term recursion. This is actually the exponential with respect to this associative product and this pre-Lie Magnus expansion, okay? Another remark, actually, there's to those of you who know a little bit about numerical analysis, there's the fair expansion where we can actually write the solution of such a recursion as this product of exponentials. And here again, you take the original expression of fair and you somehow try to identify the pre-Lie structure. Now, let's introduce a little bit of notation. Now here by this brackets, I mean simply the left iteration of n R maps, okay, so where the R maps are somehow concentrated on the left. And here, when curly brackets appear, we mean the same, what I call a Rota-Baxter word, a strictly iterated Rota-Baxter word, and the R maps are concentrated on the right. Remember that we are after these type of recursions. I mean, I'm playing something a little bit around with this minus and the plus sign here, but it's not really important. You can simply redefine A, okay? Then the formal solution is, of course, written in terms of these so-called Rota-Baxter words. And you remember also that we had this natural factorization of this element 1 minus A in terms of the inverse of x and the inverse of y. Here I remind you of the expression for y inverse and x inverse. And in fact, putting ourselves into the context of free Rota-Baxter algebra, but I don't want to go into this, you can define on these Rota-Baxter words actually a Hopf algebra structure in terms of divided powers. We call this the free non-commutative Spitzer algebra on one generator. what's good for is, remember we had this series, and this was like this group-like element, right? We wanted to invert this sitting inside the group. And first of all, knowing the inverse already, which is defined actually in terms of y, so where the R tilde map appears, we can define the antipode. So it actually gives them really all we need to define this Hopf algebra. And you see it's a little bit complicated, but we can use this to define a certain initial value problem for x. And this we do in terms of the so-called Dünken map. Here you see this is the convolution product of the antipode, this one here, with the grading operation, which simply, I mean, the degree here, of course, is obviously in terms of the R maps appearing here. So this is a Rother-Baxter of degree n. Again, the same here. And somehow, as this is a group-like element with respect to this co-product I introduced before, we have the following expression. So we have this is giving you the inverse of x times the grading operation applied to n. So this is what I've written down here. And you see, this is like it multiplies the Rother-Baxter work by its degree n. And what you can show is if you work this out with this so-called Dünken map applied to such a Rother-Baxter word of degree n, that the image is this left iterated pre-Lie word. Okay, so here we have the map R. You apply this to a particular element in this series, and you can show that the image, this is somehow the primitive elements in this Hopf algebra, is this left iterated pre-Lie Rother-Baxter word.
Remind me of the meaning of the capital N.
It's simply multiplying by its degree.
Oh,
It's a grading operation, right? So then there are a couple of, there are now interesting identities. They might look a little bit unfamiliar, but from the commutative context, this is really simply the non-commutative generalization, which will lead to a non-commutative version of the Bohm plus Spitz identity. So it simply means we can write such a Rother-Baxter word of degree n as a certain linear combination of products of left iterated pre-Lie words with these particular coefficients appearing here. So that we actually can write x, which was the solution to this recursion we are looking after. You see this is here, this sum, actually becomes the sum of these linear combinations of left iterated pre-Lie words. So it's a rewriting, essentially. Here I've taken out the R map, which you can see overall all of these capital C's are actually lying in the image of R. And I take out R, and so I have to replace the ordinary algebra product by the double Rother-Baxter product. And so now let's take such an n-fold iterated Rother-Baxter word. We can write this actually as this linear combination of left iterated pre-Lie words. And this actually leads then to what we call the non-commutative Bohm plus Spitz identity, where again on the left-hand side now we take here n different elements, we operate with the symmetric group on it, and then we can rewrite the whole thing on the right, where there's no iteration anymore involved, so to say. It's simply in terms of the associative of the double Rother-Baxter product or the pre-Lie Rother-Baxter product. And when you have to put this here, it's a little bit on the statistics of these permutations. It's not too complicated, but I don't want to go into this now. But this is really the non-commutative version in the sense that if you make your algebra commutative, you somehow forget about brackets, you essentially get back the commutative original Bohm plus Spitz identity. All this, essentially this pre-Lie product simplifies to the ordinary algebra product, but you have the thetas appearing here. Okay? So again, we had this x, which was the solution for this recursion in the Rother-Baxter algebra, formally written in terms of the linear combination of these Rother-Baxter words. We have seen that we can write this as the exponential of R of this pre-Lie Magnus expansion. Here I remind you of this pre-Lie Magnus expansion with the pre-Lie operation here. And the grading operation, now we can make it explicit by simply introducing a parameter t, okay? And then we apply t d dt, which simply multiplies this Rother-Baxter word of degree n by n. Okay? So essentially, then going back to this Dünken operation, which was actually taking the inverse of x times the grading operation applied on x, and then on the right-hand side we get the sum of this left pre-Lie words. We can transfer this into an initial value problem here. This is a simple differential equation. here by psi I mean now I take this sum of left iterated pre-Lie words and I divide by t, so that you see here degree, a lowering degree. And this we can solve. We can simply solve this in terms of this explicit solution due to, I mean, I attribute it to Strichert, but maybe Libansky-Mielnik, or what's called the continuous BCH formula, where you have the strict iteration of these ordinary Riemann integrals, these particular coefficients where you have the descents appearing, respectively to this permutation, and the strict iteration of Lie brackets in terms of this psi, which is the sum of these left pre-Lie words. So that in the end, actually we have an explicit expression for the solution x of this Rother-Baxter recursion. Then going back to the problem of renormalization, remember this was actually trying to find an explicit form of this counter-term recursion. Here this was this element A which appeared before. So that actually the solution, of course, is this iteration of Rother-Baxter words. Then remember these psi's. And so we have actually then find an explicit expression in terms of the exponential and this continuous BCH formula. I mean, the complexity is, of course, included here in this pre-Lie Rother-Baxter words. Thank you.
Kurusch heroically finished before his time was over, and so we have a few minutes for questions.
Yeah?
When you iterate the Rother-Baxter algebra, is there any relationship, like inclusion between the iterated algebras and the original ones?
What do you mean by iteration?
Well, you had double Rother
Yes.
algebra, and then you can create further Rother-Baxter algebras. Is there any relation between algebras?
Well, I mean, if the Rother-Baxter map is idempotent, for instance, then this hierarchy stops after 2 cycles, right? Essentially, you get back your original Rother-Baxter algebra. But in general, I don't know. I didn't think about this. Okay. One more question. One more question.
You normalized everything?
The point was that the problem of renormalization is the solution to this algebraic equation. That it was, or the explicit form of this algebraic equation.
So there was a letter circulating for Pierre Leroux's family. Is that still here somewhere? Okay. Made it around. Everyone should take an opportunity to fill that out. Let's take a 5-minute break and we'll resume at 1:15.